Okay, so we're finishing 1-3. I guess this is part 3 because we did the first part in 2 parts. So this is the last part, piecewise functions. And these are functions that we'll see kind of readily in calculus. So real simple, when we're talking about a piecewise function, it's just a function that is 2 parts. So maybe you have the line x minus 2 for x less than 1, then maybe you have the parabola x squared for x greater than or equal to 1. Okay, so the first thing I want to do is give you the idea of the graph. Well, what does the graph look like? I call this top branch, lower branch, okay, but it's just basically how can we take a piece of one function, a piece of another function, and put it in one graph. That's basically what we're doing, okay? And then we'll look at the type of evaluations that you'll be asked to make. So here's what this is saying. Part of this graph is a line, and it's the line x minus 2 for x values less than 1. So basically, here's what I do. Wherever this is kind of like your boundary, it says graph this line all the way up to 1, but stop it before you get to 1. So what I'll do is I'll plug this 1 in, and I can see it's the point 1, negative 1, and I'm going to put an open circle by it. So that way it helps me visualize, okay, that line, x minus 2, well, I know it's got a y-intercept of negative 2, and I know that at 1, negative 1 is where I'm cutting it. And it says for x less than 1. So I want the part of the, so this line technically goes like this. All right, goes like that forever. But I want the part left of 1. So I'm going to erase this part because this constraint right here tells me to only keep this part of the line, a piece of the line. Okay? In this right here, what we're doing is restricting the domain for that part of the graph. Now, obviously, you can see the entire domain is used because now it says for greater than or equal to 1, draw the parabola. So now I'm going to draw the parabola x squared for the next part. And again, 1 is the critical changeover. It won't always be 1. It could be 5. It could be 2. It could be 0. You could have 3 branches, which I'll show you. So I can see that this graph has the point 1, 1, and it would be a closed circle because then it can equal to 1. So I'll go to 1, 1, put a closed circle. And now I know the parabola typically does this. Right? That's what an x squared does. But I can't keep the entire picture because if I keep the entire picture, is this really a function? No. Because why not? Why is it not a function? Yeah, right here you're going to have 2 outputs, right? So it fails the vertical line test. But again, I've got to do what it says. It says keep the part for x greater than or equal to 1. So again, right here is where I kind of cut it, and I'm going to keep it right of that, greater than or equal to 1. And now you can see where one stops, the other one starts. Okay? That's a piecewise function. All right? Okay. So the term piecewise is used because why? Why do we use, what's the logic there? Pieces of different graphs, that's exactly right. But it is a function, so there's no overlap. And notice, if this is a closed circle, this can't be a closed circle, because again, right there you would fail. So if one's closed, one's open. All right, so that's the notation. And then what you're going to be asked to do is you're going to be asked to evaluate. So maybe it's part A, might be like find f of negative 2. Well, the instructions tell you which one to plug it into. The instructions are clear. Negative 2 is in place of what? X. If x is less than 1, you use this. If x is greater than or equal to 1, you use this. Well, which one do I use, top or bottom? The top. And you plug in and you get negative 4. And then that should make sense because if I go to negative 2, my y should be negative 4 down here. There should be only one output. Okay. All right, so I'll put some more answer those three real quick. See if it's showing up on there. It's got a little bit of a glare. Answer those three. Okay. So let's go through. We'll ask Andrew, what did you get for f of negative 1? Negative 3. It's Andrew, right? Okay. Andrew, you tell us, what did you get for f of 1? 1. Right, because I have to plug in here. And f of 4, Kane? 16. Very good. Pretty simple, right? Everybody good with that? Okay. You don't necessarily have to graph them, but I just want you to be able to visualize. What you need to be able to do is evaluate them properly. Then I'm going to show you one that has 3 branches. And then I'll show you what might be a question we'd have in calculus, and we'll leave that as a challenge problem for you to try between now and next class. Okay, we won't solve it today. I'll just pose it, and then we'll see if you can figure it out. Okay, and it's not, this challenge problem is not in your My Math Lab, in your course numbers. It's just extra. Okay, let's try another one. So, what else could happen? Okay, what other scenarios might there be? Well, we could have this. We could have, we'll call this example 2. It doesn't always have to be f, it could be g. I could say g of x equals, okay? But we typically use our function notation. And maybe I'm going to use negative 2x for x less than or equal to negative 2. 5 for x greater than negative 2 less than 3. And x plus 1 for x greater than or equal to 3. All right. So we're going to do a couple of things here. So first, just even though maybe it's not required, we're going to try to sketch this. Second, we'll answer some questions. We'll find g of negative 3, g of 0, and g of 5. We'll find those 3. The next thing we're going to do is think about what's the domain and what's the range for g. We're going to do those 3 things. Probably I'll have to put the sketch maybe over here. Okay. So, see if we can sketch it real quick. Can you, how do you graph 5? How do you graph g is 5 from negative 2 to 3? More than dots. It's a horizontal line at 5. It's just saying, because there's a whole bunch of x's in here. See, from negative 2 to 3, there's a lot of points, right? So on that stretch, the output's always 5. However, think about what you're going to have to put here. If it's greater than negative 2, less than 3, you can't put a closed circle. But 5 means this horizontal line 5. Your output's always 5. See if you can make a sketch. So this has 3 branches. How many branches could we have? What do you think the answer to that is? As many as you want. But in order to keep it a function, you got to make sure that there's no overlap. So what I would do is, the first thing I would do is I'd say, okay, I can see that this graph has the point -2 forward, and it should be a closed circle. That's where this one should end, because all I did is plug the -2 in. So now I kind of know where that one ends. Okay. Okay. So let's get started. So first thing I'm going to do is draw the line -2x left of -2, so it'll be this part. How do I know it's that part right here? How do I know this is what the line is doing? Because I know the line -2x. You need to know these lines. Negative slope, -2 means it has a negative slope. It goes like this to the origin. Right? Yeah, I can picture the whole line, and then I'm cutting it. 5. So from -2 to 3, I'm putting open circles there because it's greater than -2, less than 3, and there's the line 5, horizontal line. Now I've got the first two pieces. Okay? So I know that this should have the point -2, 5, open circle, 3, 5, open circle. This should have the point 3, 4, closed circle. How did I get 3, 4? Yeah, plug the 3 in, because that's where this line starts. So I'm visualizing the line. What does x plus 1 look like? Can you finger draw it? Yeah, like that. What's the y-intercept? 1. So I know that this line looks like this. But by putting the point 3, 4 there, then I just now continue the picture, and I know to go right. See? Here's my picture. Because x plus 1 is this entire, it's this entire thing. But I can't draw all of it. So if I draw all of it, it's not a function. I know which part to draw. Greater than or equal to 3, which I did. Boom. All right. So that would be the picture. Okay? And that is called piecewise discontinuous. This is a piecewise discontinuous function. What do you think continuity means in math? Because this is where I'm trying to connect it to calculus. What do you think a graph is continuous? What do you think that means? Right, this one goes forever, doesn't it? Goes forever to the right, goes forever to the... That's exactly right. She said it has a little break in it. Continuity means, can you draw the whole graph without picking up your pencil? I can't, because I got to jump right here. Okay. All right. So that's the sketch. So now can you evaluate each of these? So take a second, and now you got to know which one to plug into. Here's the instructions. X is less than or equal to -2, plug in here. X is between -2 and 3, plug in here. How do you plug in if there's not an X? It's 5. All right, you can see. X is greater than or equal to 3, you plug in here. All right, so what do you get on your outputs? What's G of -3? 6. What's G of 0? What's G of 5? 6. I didn't find it like that. Just worked out. Okay? Everybody with us on which one you're plugging into? What's the domain? All right, well, what about this hole right here? You don't have this point. That's exactly right. You still have the 3. So the domain is all real. How do you write all real in interval notation? Infinity to infinity. Very good. What's the range? This one's not as, you gotta look a little bit, right? 4 to infinity. Everybody see that? Because 4 is the lowest it goes. Before. Very good. All right. Excellent. Okay. So the graphing may not be the easiest part with the piecewise, but you know, I'm just trying to help you visualize. This is the last two things are the things you're going to be asked to do. I think that if you have the picture, it makes it easy, because it really makes it easy to do domain and range if you have the picture. Okay? All right. So, any questions about piecewise? All right. Okay. So I'm going to show you a connection to calculus. I'm going to give you a challenge problem, and we'll talk about this next time, see if you can find the answers, okay? I'll pose the question, I'll point you in the right direction, but then the rest is up to you. All right, so CTC, connecting to calculus. All right, so we just throwing these in. This is, you don't have to do it. This is a challenge. All right, here we go.
Teachers, pardon the interruption. The water in the main building will be turned off at 10 o'clock, so you got a couple minutes warning. Shouldn't be any more than 30 minutes, and we'll let you know when they turn it back on. Just in the main building. Thanks.
Okay, there you go. This is a piecewise function with 3 branches, 7, ax plus b, and -7. So what we're going to go ahead and do, I'm going to just, before I pose the question, because the question is going to go here, let's at least draw what we know. So what does 7 look like for x less than or equal to -2? We should be able to plot that. What does 7 look like for x less than or equal to -2? Very good. So go to -2, right? That's where it cuts. Go up to 7. There's that. Which way do I graph? Left or right? Left. That's exactly right. So that picture goes with the top branch. Because it's the line 7 for x less than or equal to -2. So left of -2. Now, use that help to graph the bottom part. Don't worry about the middle because we don't have any numbers. You can't graph the middle, but you can graph the bottom. And then I'll pose the question. This is a calculus problem. This is, once you see the question, it involves calculus, but you don't need calculus to do it, really. It's just something we study in calculus. So where's the next place I'm going to go? X is what? 5. Y is what? All right, I'm going to put a dot there, close circle right. And which way am I going to graph now? To the right, very good. All right, so that's the picture we have. What's unknown is this. What do you think this is the equation of right here? Ax plus b. A linear function, that's exactly right. A linear function. And the question is this. What do the constants a and b need to be such that f of x is continuous? So, because it's calculus, it can get a little wordy. ST I use for such that. So picture this. This is a linear function. Here's what basically it's saying. I'm just going to draw and then just like a highlight one here. So this is the piece that's missing. We don't know where it goes, right? It depends on what the slope is, it depends on what the y-intercept is. You know those little toys that the kids can snap together? They're like these, like rods or these, they're not like Legos, but they're a little different where it snaps and one part has an open spot and one has, it snaps in. That's what we need to happen. What we want is, we want this graph to be continuous, which means no what? What was the word that we had used earlier? No breaks, no gaps, right? So this open circle needs to be exactly right here at this point. What point is this right here? So we need that open circle to be at -2.7 there, and we need this open circle to be where? And it won't be open because it'll snap together. Then we need this line. We need to know what that line is. So we need that part to be at 5, -7. So notice, I know this is a linear function and I know the 2 points that I need on it. Thus, with that information, could you figure out what your slope needs to be and your y-intercept given 2 points? Solve for A, which is the slope, and B, the y-intercept. And if you did, if you can, now you are finding the line that needs to go there, and that's your challenge problem for Wednesday, or sorry, for Thursday. We're gonna stop there because I want you to finish it. Okay? And then if you can figure out what it needs to be, and then it connects perfectly, that now would be a continuous function. And that's something that we look for in calculus. We study continuity. All right, that's it. So that's extra. So we'll look at this. It won't be in your My Math Lab. For you guys at home, second, third, and fourth period pre-cal, work on this, and then maybe we'll film the solution, what the solution is to that question. So that's it. For 1.3, you should be able to finish that assignment. It's due tomorrow night, and then we'll get a little bit of 1.4 out a little later today. Good, everybody good? Trying to.